Alright guys, welcome to Theorems about roots of polynomial equations. So the big thing you have to understand here is that the factors of the numbers of a sub n and a sub 0 in this polynomial can help you factor and solve polynomials of p of x equals 0. And what that means is that if you take the constant term and the leading coefficient and work with them, you can actually find possible roots and to help you solve and factor polynomials. And that's where the rational root theorem comes in. And the rational root theorem is actually taking the factors of a sub n, the factors of the constant term, and dividing those. All those factors are going to be divided by all the factors of the leading coefficient, and those become your possible zeros, your rational roots. The downfall here is it only gives you rational numbers. Okay, so it's not going to give you anything, like pi, anything that's non-terminating, non-repeating. Okay, so irrational numbers it doesn't work for, and it doesn't show you imaginary possibilities, only rational roots. Be sure to reduce everything in the form p over q to the simplest form. And integer roots must be factors of a sub 0. So the integer roots must be factors of your constant term. So let's look at an example and see what this means. Okay, so we're going to use the rational root theorem to list the possible roots of this polynomial. So the idea here is you try to factor this and you can't. You can't group. This is not quadratic. How do I factor? Where do I start? Well, you start by listing all possible rational roots. To do that, you take the factors of your constant term and divide all of those by the factors of your leading coefficient. My constant term is 5. The factors of 5 are plus or minus 1, plus or minus 5. 2 is my leading coefficient. The factors of my leading coefficient are plus or minus 1 and plus or minus 2. Now, you really can just leave off the plus and minuses until the end if you're getting confused. Okay? But what's the idea here is I kind of make a spider web. Each of these constants have to be divided by each of these leading coefficients. So 1 goes with divided by 1, 1 divided by 2, 5 divided by 1, 5 divided by 2. And those are the possible roots. 1 divided by 1 is 1. 1 divided by 2 is 1/2. 5 divided by 1 is 5. 5 divided by 2 is 5/2. And just put plus or minus with all of those. Because the idea is 5 is equal to 5 times 1. But it's also 5 is also equal to negative 1 times negative 5. So you have to include the pluses and minuses. And that's the rational root theorem, listing all possible rational roots. So the things you have to watch out for, none of these could be roots. They're just possible roots. So you have to be careful. The rational root theorem helps you find all possible rational roots, but it doesn't guarantee any of the ones that you find are actually roots or zeros of your polynomial. Now in example 2, I've done the same thing. What are the rational roots of this polynomial? It's a third degree. But I've actually taken it a step further and actually factored this polynomial and found the zeros. So I list the constant term, that's 2. The factors of 2 are 1 and 2 and plus and minus. Leading coefficient is 15. List all those factors, 1, 3, 5, 15. Plus and minus each of those. Okay? So now each of the constant term factors have to be divided into all of those. So the idea here is 1 divided by 1, 1 divided by 3, 1 divided by 5, 1 divided by 15. 2 divided by 1, 2 divided by 3, 2 divided by 5, 2 divided by 15. And you see all those here. 1 plus or minus 1/3, 1/5, 1/15, 2, 2/3, 2/5, 2/15. And all of them are plus or minus. I went a little further. Okay? And I checked one of my zeros, my possible roots. I checked 2 over here. Positive 2, and I use synthetic division, and I have a remainder of 0. So if 2 is a 0, x minus 2 is a factor. What's left? Remember, remainder, constant, linear, quadratic. So I have a quadratic polynomial. That factors, using our techniques from chapter 4, into 5x plus 1 and 3x minus 1, giving me the zeros of 2, negative 1/5, and 1/3. And it just goes to show you that, in this case, all 3 zeros are in that list of possible zeros or roots. So rational roots, please remember that. Those are zeros, okay, x-intercepts, they all mean the same thing. Now, as mentioned in class, there's one other property I didn't list on here. It's really conjugates. Conjugates always come in pairs. So when we solve quadratic equations that had no real zeros, you got a plus and a minus. Same thing here. If you have complex roots, they always have to come in a pair of 2. Okay, so here in this example, what is the third degree polynomial with roots of -4 and 2? So that's interesting. I need a cubic, okay, and I need, that's a third power, so there's going to be 3 roots. Whether they're all real, 1 real, 2 imaginary, I don't know. But let's look. I have 1 real root, and 2i here is imaginary. So let's know if those are zeros. If -4 is a 0, x plus 4 is a factor. If 2i is a 0, x minus 2i is a factor, and in red, x plus 2i. There's the conjugate. There's the pair. When you multiply those together, you get x squared plus 4, and then you're going to multiply that to x plus 4, and then distribute again, and you get x cubed plus 4x squared plus 4x minus 16. So this was another property I didn't write, but the idea is that zeros, if they're imaginary, have to come in conjugates. They have to come in pairs of 2. Okay? And I wrote those here, and then you just multiply out like we've done before. Our last example deals with this guy, Descartes' rule of signs. Okay, and there's 2 possibilities. So the rule of signs here, this tells you the number of possible positive real roots or the possible negative real roots. Kind of like the rational root theorem. They're possibilities. Okay, so here's the idea. If you look at your function p of x and you count the number of sign changes. Okay, so the number of positive real roots, and that's key here, the positive real roots of a polynomial is either equal to the number of sign changes or is less than that by an even number. I always use 2 as an even number. That way I'm ensuring to get all possible cases. The number of negative real roots here, you got to be careful. The negative roots, as you change x to negative x, is either equal to the number of sign changes there of p of negative x or less than that by an even number. So let's look at an example of what this actually does. So with Descartes' rule of signs, this won't tell you the zeros. It's not going to list all possible zeros. It's going to tell you the possible positive real roots and the possible negative roots. So it will not tell you if there's imaginary. Okay, just the number of positive and the number of negative real roots. So if we look at what does the Descartes' rule of signs tell us about this function? Well, if I look at the function, I go from a positive to a negative. That's a sign change. So there's 1. And then from a negative to a positive, there's 2. 2 sign changes. So the theorem tells me that, okay, there can be 2 positive real roots. But if I subtract 2 off that number, there also could be 0 positive roots. Okay? Now, p of negative x of that function, I substitute negative x and I simplify. I see 1 sign change. That means there's 1 negative root. Now, I can't subtract off an even number there because if we were counting the number of roots, you can't say I counted -5 roots. It doesn't make sense. Just like distance can't be negative. When you're counting the number of possible roots, that can't be negative. So we just say 1 negative root and that's it. You don't subtract 2 off there. If this was 2 or 3, okay, any number of sign changes greater than 2, greater than or equal to 2, then you start subtracting off that even number. All right, guys, so that is theorems of polynomial equations. If you have questions or comments, just type them below or email me at nicholas.bennett@dc.gov.